In today's video, we will look at the area problem. And this serves as an introduction into the final topic of this video series, which is the integral. And so in this video, what we're going to do is we're going to actually state what the area problem is, and then look at how we can solve it. In doing so, we're going to see what a Riemann sum is, and then see what a Riemann integral is. Before we can even define the area problem and look at it, we're going to need some notation first. And the first notation we're going to look at is summation notation. Right now, if we want to add several terms together, it's often tedious to write out the entire sum, so we shorthand it, and we do so using this symbol, which is the Greek letter capital sigma. Right, so for example, this sum right here, the sum of the first 10 positive integers, can be represented like so. Right, now this is read the sum from I equals 1 to 10 of I. I is known as the index of summation. And really, it's more of a placeholder. It's a dummy variable. Now, we're also going to need some properties. So if we take the sum from I equals 1 to some positive integer n of some constant c, then this is just n times c, right? It's c plus itself n times. If we take the summation I equals 1 to n of c times a sub I, then we can factor the constant out. Right? And this is the law of distribution from algebra. And if we take the summation of a sum or difference, then we can write this as two separate summations. Right? And this is the idea of associativity of addition and subtraction. Now, there are going to be several useful sums that we use, 3 in particular. So it's important that these are written down somewhere for quick reference. The first is the sum from I equals 1 to n of just I. So the sum of the first n positive integers is n times n plus 1 all over 2. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6. And finally, the sum from I equals 1 to n of I cubed is n squared times n plus 1 squared all over 4. Right, again, these are 3 very useful sums. I recommend that you write them down somewhere for quick reference. We can now take a look at the area problem. Right? So the area problem is really just approximating the area between the x-axis and the curve of a positive function f of x over some closed interval, right, which has the form a to b. This is all the area problem is. Right, so if we go ahead and graph it, right, we have, I don't know, some function. Something like this. Right, this is the point A. This will be B. Right, and then what we want to do is find that was awful. There we go. And we want to find the area then of this shaded region, right? Now, this is not a region that was studied in geometry. So we don't have a nice geometric formula for this. So how do we go about tackling this? Well, what we do, divide this region into n subintervals of equal width. Call that equal with delta x, and since it's equal, it'll be the length of the interval divided by the number of subintervals. Right, these intervals, or these subintervals, are obtained by selecting equally spaced points such that A is x naught, right? So that's our first point. Then we pick an x1 that's larger, then we pick an x2 that's larger still, and we keep going until we reach our final point, which happens to be the end point. Right. Now each of these points is an endpoint of a subinterval. And notice that since they're equally spaced, each xi, right, so each point is the point before it plus delta x, or we can also write xi is the left endpoint, our starting point A, plus I times delta x for 1 less than equal to I, less than or equal to n. This choice of points is called a partition. And we will now formally define a partition. A set of points, call it P, equals x sub I, for I equals 0, 1, 2, up through n, with A equal to x0 less than x1 less than x2, so on and so forth, less than xn, which is B. Which divides the interval A to B into subintervals x0 to x1, x1 to x2, xn minus 1 to xn is called a partition of AB if all these subintervals have equal width, then the set of points forms what we call a regular partition. Of the interval AB, right? So if all of the subintervals have equal width, which is how we defined it up here, then it's a regular partition. Now, once we have formed our partition of the interval, we can create n rectangles. Right? So essentially what we've done is, once we've divided our partition up, we have created n rectangles, as so. And this one I drew too high. We'll just say it stops there, let's say. Well, then the general idea is that the total area is approximately the sum of all the areas of these rectangles, right? Now, each rectangle will have an area, call it a sub I, to represent the area of the ith rectangle. And remember, it is width times height. Right? Well, width is the length of the subinterval, which is delta x. Now the height. To determine height of a rectangle, right, depending on how you want to draw it, we just take any point in the interval and evaluate it at that point. So we'll say c sub I, where c sub I is any point in the interval x sub I minus 1 to x sub I. Right, the total area would then approximately be the sum of all these areas. And there's three standard ways to pick these points c sub I. You can pick it however you want, but there are three very commonly used methods of picking the c sub I. The first method is to let c sub I be the right endpoint of the subinterval. Right? If we do this, we get what's known as the right endpoint approximation. And that is given by r sub n equals delta x times the summation I equals 1 to n f of x sub I. The second method is to let c sub I be the midpoint of the interval. This gives us what's known as the midpoint approximation. And that is given by m sub n is equal to delta x times the summation I equals 0 to n minus 1 of f of x sub I plus x sub I plus 1 all over 2. And the final method is to let c sub I be the left endpoint of each interval. This gives us the left endpoint approximation I don't know why I wrote approximations. And that is given by L sub n is equal to delta x times the summation I equals 0 to n minus 1 of x sub I. Regardless of how we choose the c sub I, we still get a summation. And we call this particular type of summation a Riemann sum. Right. So we say let f of x be defined on a closed interval a to b, and let P be a regular partition of AB. Let delta x be the width of each partition, or I'm sorry, not partition, of each subinterval xi minus 1 to xi, and for each I let xi star be any point in the interval xi minus 1 to xi. The sum that is given by summation I equals 1 to n f of x sub I star times delta x is called a Riemann sum of f of x. We can now solve the area problem, right? So recall that the Riemann sum gives us the sum of the areas of the rectangles, which is an approximation of the area under the curve. However, this approximation becomes much larger, or much better rather, as we let the number of rectangles increase to infinity. So if we take the limit of this sum as n goes to infinity, we would get the true area under the curve. let f of x be continuous, non-negative function on an interval a to b, and let this sum be a Riemann sum for f of x. Then the area under the curve y equals f of x on AB is given by A equals the limit as n goes to infinity of that Riemann sum. Now there is a useful property, which is a direct consequence of this definition, and that is specifically that the limit as n goes to infinity of the right endpoint approximation equals the limit as n approaches infinity of the midpoint approximation, which equals the limit as n approaches infinity of the left endpoint approximation. Right, so it doesn't matter which Riemann sum we use. When we take its limit, we'll get the same value. Right, since all of these approximations will converge to the same value, typically we take the right endpoint approximation as our Riemann sum. Although this can change depending on the function, right? So we'll typically use the approximation that is most convenient. We now define the Riemann integral. If f of x is a function that is defined on an interval a to b, the Riemann integral also sometimes just called the integral of f from a to b is represented this way. And this is read integral from a to b of f of x dx, and it is the limit as n goes to infinity of the summation I equals 1 to n f of xi star delta x if this limit exists. If it does exist, we say f is Riemann integrable, or simply just integrable, on the interval a to b. Now, this is how we defined area under a curve. So, the Riemann integral measures a signed area meaning we have something like this. The Riemann integral over this interval is assigned area. So this area here would be a positive area. This area down here would be a negative area. And if these two areas happen to be the same, the magnitudes anyway would be the same, then the Riemann integral total would be 0. Right now, some properties of Riemann integrals. If we take the integral from a to a of f of x dx, this is just 0. The integral from a to b of f of x dx is equal to negative integral b to a f of x dx. Then we have the integral from a to b f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. The integral from a to b of c times f of x is equal to c times the integral from a to b of f of x dx, where c is any constant. And finally, the integral from a to b of f of x dx, we can split the interval at c and then say this is the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And finally, we have some comparison theorems. So if f of x is greater than or equal to 0 over the interval a less than or equal to x less than or equal to b, then the integral from a to b of f of x dx is guaranteed to be greater than or equal to 0. If f of x is greater than or equal to g of x over the interval a less than or equal to x less than or equal to b, then the integral from a to b of f of x dx will be greater than or equal to the integral from a to b of g of x dx. And finally, if we have constants little m and big M, such that little m is less than or equal to f of x, which is less than or equal to big M, over the interval a less than or equal to x less than or equal to b, then little m times b minus a will be less than or equal to the integral from a to b of f of x dx, and that will be less than or equal to big M times b minus a. Now let's look at some examples. First, if we look at the function f of x equals x squared over the interval 0 to 2. What we want to do here is we're going to find R4, M4, and L4. Right, first, take a look at the graph. If we sketch the graph, and let's say this point here represents x equals 1. And we'll say this point here represents x equals 2. Right? Then what we're finding is we need to divide this into 4 subintervals, right? And that interval really does not look right, does it? Let's fix that. Let's make this point 1 instead. I actually don't need these values. So we're going to divide this interval 0 to 2 into 4 subintervals. Right? So our capital N is equal to 4. Then our delta x is 2 minus 0 divided by 4, which is 1/2. Right? Our starting point is 0. Then x1 will be 1/2. x2 is 1. x3 is 1.5. x4 is 2. For the endpoints, right, if we first look at R4, we're using the right endpoint as our height, right? This will probably be 1/2 here. Then this is our 1. This will be 3/2. And then, of course, a final endpoint is 2. So these would be the 4 rectangles for R4. Let's now look at L4. Right? We will go 0 to 1/2, right? Then we use the left endpoint of each height. Right? So we do that. And then we would do this. These would be the rectangles we get from L4. Right? There's only 3 of them. And finally, for M4, we take the midpoint. Right, so it'd be something like that. Like that. And then like that. So these would be the 3 rectangles we get from the midpoint approximation. Alright, so let's now actually calculate these. R4 is delta x times f of a half plus f of 1 plus f of 3 halves plus f of 2 right? When we actually value this out, we will get 3.75. Let's look at M4 next. M4 is delta x times the midpoints. So we'd have f of a quarter plus f of 3/4 plus f of 5/4 plus f of 7/4. This will be 2.625. Alright, so I actually need to make a slight adjustment. These rectangles are incorrect for the midpoint. Just real quick correct that. The height is based on the midpoint, right? So the height would be up here, but we would still have that as our rectangle. Here the height would be up here, right? This is the midpoint. So we go like that, and then like that. Midpoint here, height here. And then midpoint up here. Right, so the idea is, if you notice, in this case, the green is completely under the curve, the blue is completely over the curve. The orange, which is the midpoint, has some area that's over and some that's under. All right, and finally we'll calculate L4. That's 1/2 times f of 0 plus f of a half plus f of 1 plus f of 3 halves. And that is going to equal 1.75. What we will now do is take that function over 0 to 2 and calculate the actual area. Right. So we're going to use Rn. Remember, this is delta x, which is going to be 2 over n times summation I equals 1 to n of f of x sub I. So we're going to have 2 over n times the summation I equals 1 to n f of, now x sub I, recall, is a plus I times delta x. Right. In this case, our a is 0, so we're going to have I times 1 over n sorry, 2 over n. So it'll be 2I over n. So that's 2 over n times the summation I equals 1 to n of 4I squared over n squared. But that 4 over n squared is constant. So we can pull it out of the sum and we get 8 over n cubed times the sum I equals 1 to n of just I squared. That is one of those useful sums that was introduced earlier. That is 4n. No, it's not. It's n times n plus 1 times 2n plus 1 all over 6. And this simplifies to 4n times n plus 1 times 2n plus 1 all over 3n cubed. Area will be this limit. Limit as n goes to infinity of r sub n, which is the limit as n goes to infinity of 4n times n plus 1 times 2n plus 1 all over 3n cubed. And that limit is 8 over 3. So the area, this total area, from this blue line all the way to 0, is 8/3. For our third example, we're going to evaluate the integral from 3 to 6 of the square root of 9 minus the quantity of x minus 3 squared dx. Now, if we take a look and we go y equals f of x, y equals the square root of 9 minus x minus 3 squared, we'll get y squared equals 9 minus x minus 3 squared, right? Which is x minus 3 squared plus y squared is equal to 9. This is a circle of radius 3 centered at the point 3, 0. Let's say that there. Now let's say this here is our 3. Right, that is our center. I don't know, this is good enough for our circle. 3 to 6 would be this here, and since we're only looking at positive square root, we want y to be positive. So the area we're actually looking at is then this area. Right. Well, that is a quarter circle. And since the Riemann integral is area, we can say that the integral from 3 to 6 of the square root of 9 minus x minus 3 squared dx is a quarter of the area of a circle of radius 3, which is 1/4 pi times its radius, which is 3 squared, so we get 9 pi over 4. And for our final example, we're going to calculate signed area of f of x equals x minus 2 over the interval 0 to 6. We want signed area and total area. There is a difference. And if we take a look, x minus 2 would be the line of slope 1 that passes through negative 2. Alright, there we go. Now 0 to 6, let's say 6 is out here somewhere. 0 is here, so we have two areas we want to look at. We have this area. And this is, of course, a right triangle. This is length 2 here. This is also length 2. And then we also have this triangle, which is again another right triangle. Now this will be from 2 to 6, so that is length 4. This will also be height 4. For the signed area, and that is just simply an integral from 0 to 6 of x minus 2 dx. And that is going to be, since area 1 is negative, area of a triangle is 1/2 base times height. Then it'll be plus the area of that second triangle, which is again 1/2 base times height. We get negative 2 plus 8, which is equal to 6. That is our signed area. For total area, we want the function to be completely positive. So we go into the absolute value of x minus 2 dx, which is the absolute the integral from 0 to 2 of 2 minus x dx, plus the integral from 2 to 6 of x minus 2 dx. And this came from the definition of absolute value. Right, remember, absolute value of x is defined as x whenever x is greater than or equal to 0,
and negative x whenever x is less than 0. But again, it's just the area of these triangles. So it'll be 1/2 base times height for the first, plus 1/2 base times height for the second. This is 2 plus 8, so the total area is 10. And that concludes our look at the area problem. Now, you should notice that calculating definite integrals, these integrals, via Riemann sums is extremely tedious, and for a lot of functions, downright impossible. What we want to do is see if we can find an easier way of evaluating an integral. And there is. And that is what we're going to start to look at in the next series in this video. Next video in the series even. Right? We are going to, in the next video, study the antiderivative. So we studied the derivative. Now we're going to study its inverse, the antiderivative. I will see you all in the next video.